In this video, I'm going to look at how we might solve exponential functions using logarithms. What I mean by that is, if I've got an example, say 3 to the power of x is equal to 9. This here is what we call an exponential function. What makes an exponential function is our unknown is a power. So we're wanting to know what power would we need to raise 3 to equal 9. Now in situations like this, it's a nice simple solution, so we can find it through the process of equating indices, which I showed you earlier. We can simply rewrite 9 with a base of 3, so saying that 3 to the power of x is going to be equal to 9 written as a base of 3 is the equivalent of 3 squared. Now when our bases are the same, we know that the exponents are equal. So we can therefore say our x here has to be equal to 2. Now this process is great when we've got a simple solution. But what if I had a question, say 3 to the power of x is equal to 50? Well, 50 can't be written with a base of 3 easily. So we need another process of which we might be able to use to be able to find our unknown value of x. We can probably determine what the value of x should be between. So for example, 3 cubed would be 27. 3 to the power of 4, well that's 27 times 3, which is 81. So because 81 is greater than 50 and 27 is less than, our value of our x should be between the power of 3 and the power of 4. But I don't really know where it is in between. So this is where logarithms come in handy. What I do with a statement like this is I do a process called taking the log of both sides. Essentially, I'm raising both sides to log. So I rewrite this as the log of 3 to the power of x. And I make this equal to, because whatever I do to one side of the equation, to keep it balanced, I must do the other. So it's going to be equal to the log of 50. And what this enables me to do now is enables me to apply my logarithm laws to isolate my x on its own. So this here, applying our power log law, can be rewritten as x multiplied by the log of 3, and that's going to be equal to the log of 50. And now I can really isolate the x on its own, because this is x multiplied by the log of 3, remembering that the log of 3 is just a number of some kind. Now, because it's multiplying, I need to do the opposite. I need to divide this side by the log of 3 to cancel it out. But whatever I do to one side of the equation, I must do the other. So if I divide both sides by the log of 3, the left-hand side is left with x. The right-hand side is going to have the log of 50 divided by the log of 3. Now, this here is the exact solution for my value of x, for my power of x. If I wanted to know approximately what that value of x is, I can now put it into a calculator. I can put the log of 50 divided by the log of 3. And what I'd get is the value of x, which is approximately equal to 3.56. Now, because this is an irrational number, if you want the exact value, you need to leave it in this format here. But if you wanted to know this value as an approximate decimal, then you can use your calculator. So now I've done that, let's take a look at another couple of examples. Let's say I have 5 raised to the power of 2x, and that's equal to 100. Well, our first step is to take the log of both sides. So that means that this is going to be the log of 5 to the power of 2x, and it's going to be equal to the log of 100. Now immediately notice I've got the logarithm of 100. This here can be simplified quite easily. What I'm looking for is, because this is a log base 10, I'm looking at what power would I need to raise 10 to get 100? Well, I know that 10 squared equals 100. So I can rewrite this as the logarithm of 10 squared. Now, of course, because this base is the same as the log, these cancel out and it's going to equal 2. So the right-hand side here equals 2. Now the left-hand side, I'm going to apply the log law again, like I did over here. So this is going to be 2x log 5 is equal to log of 10 squared, which we can just rewrite as 2x log 5 is equal to 2. But now I've got 2x multiplied by the logarithm of 5. So if I divide both sides by the log of 5, I'll find that 2x will equal 2 divided by the log of 5. But now I need to isolate x on its own. So I need to divide both sides by 2. So my x is going to be equal to 2 divided by 2 log 5. But I can also see here that these two will cancel. 2 divided by 2 will equal 1. So therefore, my x value is going to be 1 divided by the logarithm of 5. Now, of course, if I wanted to find the decimal value like I did previously over here, I could enter this into the calculator and find that. But this value here is in simplest form in terms of log, and it will give me that exact value for my x. But let's take a look at one more example here. Let's say instead of 5 or 3, let's say I've got a base of the natural exponential of e. And that's going to be e raised to the power of x is equal to, say, 50. Well, we're going to do the same thing as we did before, but instead of taking the log base 10 of both sides, I'm going to take the natural log of both sides. So this is going to be the natural log of e to the power of x is equal to the natural log of 50. And now I can use my log laws like I did before. So this here will be the x natural log of e is equal to the natural log of 50. And now, like I did before, I'm going to divide both sides by the natural log of e. So my x here is going to be equal to the natural log of 50 divided by the natural log of e. Now, at this point here, we should really note that the natural log of e is equal to 1. So we can simplify this one step further by saying that x is going to be equal to the natural log of 50 divided by 1, which is just the natural log of 50. So in summary, if we've got an exponential function where the unknown is an exponent, we can take the log of both sides to be able to then use our log laws to isolate the x and find the solution.